Today's 3 questions. What is the decibel? What is amplitude? And what is dynamic range? And how do those things correlate? Hello everyone, and welcome to WavSpot. For those of you who don't know me, my name is Austin Knaus, and I've been working with audio for the past 20 years. I started my professional audio career as a radio station engineer at the age of 17. By the age of 22, I had made my way into electronic music production as well as live performance, touring as an opening DJ for major labels, and playing for music festivals such as Dance Festopia and Backwoods Music Festival, just to name a couple. After live events took a hit in 2020, I ended up selling my entire music studio and starting a more stable career path as a technology specialist for Shure microphones. I also represented a multitude of other brands such as Klipsch speakers, LEA amplifiers, Listen Technology, Rain, and Denon Professional. Now, here in 2024, I fly all over the U.S. commissioning C-suite and executive level conference rooms for some of the top-ranked Fortune 500 companies, and I haven't even graduated high school. I'm taking everything that I've learned and boiling it down to the basic fundamentals in hopes to give you a fast track to a better understanding of the world of sound. So, let's dive in. So today we're going to be talking about the decibel, we're going to be talking about dynamic range, and we're going to be talking about amplitude and how those things correlate and commingle together. So if you remember our discussion about frequencies, we learned that they contain a positive and a negative amplitude. Now, how do we actually go about measuring amplitude? Well, in order to understand the measurement of amplitude, we need to understand what the decibel is. So our first question is, what is the decibel? So the decibel actually comes from and is named after Alexander Graham Bell, who is the inventor of the telephone, the first guy to figure out how to transmit audio over electricity so somebody else can hear it on the opposite end. The decibel, or dB, is actually an arbitrary measurement. It's arbitrary. Though there's over 8 different variations of the decibel, we're going to cover 3 of them. Actually, there's going to be a 4th, but you'll see. The 3 that we're going to talk about today are going to be the most useful and the most relevant working with audio equipment in today's world. The first one we're going to talk about is dBSPL. SPL stands for sound pressure level, and sound pressure is measured in pascals, named after Blaise Pascal, a French mathematician and physicist. So just like humans can hear from 20 hertz all the way up to 20,000 hertz, the threshold of human hearing, meaning the quietest sound that we can hear as humans, is 0.00002 Pascal. In other words, 0 Pascal is a perfect vacuum, or essentially it's outer space. There's no air pressure at all. So unlike frequencies and how they can get so high-pitched that we lose the ability to hear them, the scary part about air pressure is that there's no limit to how loud it can be. So if we know that the threshold of human hearing is 0.00002 pascals, the threshold for physical pain, like, ow, my ears hurt, is 20 pascal. For example, if you were sitting around 20 pascal, it would only take 7.5 seconds to cause permanent hearing damage. If you were to experience 200 pascal, instantaneous hearing damage can occur, but we're not even going to go there. So if you noticed, we went from 0.00002 all the way up to 20. That's actually a million. So instead of having a measurement system of 1 to 1 million, this is where the decibel comes in. The decibel is a logarithmic equation that both reduces the distance between the threshold of human hearing and the threshold of pain, and it gives us easier numbers to use. You don't need to memorize this equation, but I am going to walk you through it so you understand what's going on a little bit better. The equation for the dB is actually a 20 log multiplied by a power divided by a reference.
Oh.
Okay, let's walk through that really quick. So what is P and what is P ref? P is the pressure measured in the room, and it's measured in pascals. P ref is actually the P reference, and our reference is always going to be the threshold of human hearing, which is 0.00002 Pascal. Okay, I'm going to walk you guys through this equation really quick so it makes a little bit more sense. So I'm going to screen capture on my phone. So if we take 20 multiplied by log, And then we take the threshold of human hearing, which is 0.00002. There's 4 zeros. And then we divide that by our reference, which is also the threshold of human hearing, 0.00002. We see that it equals 0, which would be 0 dB. Now let's calculate the threshold of physical pain. So we know that the threshold of physical pain is actually 20 pascals. So if we put 20 in this equation, we can actually see this is 120 decibels, or 120 dB SPL. That's a lot less than a million. So you can see how the decibel can bring the threshold of human hearing to the threshold of physical pain to a very finite measurement. Now we only have to deal with 0 to 120 instead of 1 to a million. So what is dB SPL? It's the way we measure variations in air pressure caused by sound waves. Next, we're going to be talking about dBV or dBu. The V in dBV stands for voltage. That's right, we just went from air pressure to electricity. A better definition of the decibel is a ratio between two powers. Whether it's in voltage or in air pressure, the dB is still a logarithmic equation. So the dBV and the dBu both measure voltage. So why do we have two different measurements that measure the same thing? The dBu was actually the initial standard for measurements of electrical audio signals over the phone lines whenever they became popularized in the mid-20th century. Both the dBV and dBu use the same mathematical equation, but their reference voltages are different. The dBV became standardized after consumer electronics became more popularized, and some engineer got so frustrated and sick and tired of using 0.775 for all of his equations, he just finally rounded it up to 1 volt. Thus, the dBV became the new standard for consumer-grade electronics. What's the difference between a consumer-grade audio product and a professional-grade audio product? So check out the surround sound unit. You can see the different audio connections like HDMI, RCA. There's also that little orange digital guy on there too. And there's the connections for the speakers to go out. All that stuff is measured in voltage. It's all electricity. This would be considered consumer-grade electronics. You wouldn't find a surround sound system like this in a professional environment. If you see the RCA connectors, it's almost a guarantee it's going to be at consumer level. Other consumer-grade products are like DVD players, TVs, iPods, your phone, computers, and other devices that have either an aux cord, HDMI, or RCA, anything that does audio in a non-professional environment. Consumer line level is negative 10 dBV or 0.316 volts. This is the same voltage that's going to come out of the back of a DVD player, into a TV, out of an iPod, into some headphones, out of your computer, into your house speakers, and all the different other applications you would find in like a home surround sound system. Now, even though negative 10 dBV is a standard throughout the industry, it's very loosely held. The negative 10 dBV standard means that the electronic device can handle an audio signal around negative 10 dBV. Now, depending on how much over that is actually depending on the manufacturer's standards and what they believe that that level should be. Now take a look at this mixing console. This console uses professional line level, or 0 dBV, otherwise known as 1 volt. But you won't actually see dBV on much professional gear. What we'll actually see a lot of is plus 4 dBu, 1.23 volts. This is because the professional standard remained with the dBu, while the consumer standard changed to the dBV. The dBu is equivalent to the dBV plus 2.2, or 0 dBu is equivalent to negative 2.2 dBV. When working with professional audio equipment, you'll typically notice two different levels, mic and line. Microphones convert sound waves into electricity. A microphone can typically produce a voltage from 0.001 to around 0.01. So if we get out our calculator again, we can walk through the logarithmic equation in order to figure out what the decibel level is for any given voltage. For example, if we want to figure out what the mic level is, all we have to do is type in 20 log. Our voltage is typically 0.001 divided by our reference voltage. And what we want to use is dBu, which if you remember is 0.775. And we can see here that this is actually negative 57.78 dB. And this is our typical mic level. And side note, this is why microphones need a preamp or a preamplifier in order to get up to line level. So if you remember, professional line level is 1.23 volts divided by 0.775, which is our reference, and you can see we're at plus 4 dBu. Now I know that was a lot of math really fast, but what we need to understand is that consumer level is negative 10 dBV. Professional line level is plus 4 dBu. Professional mic level is negative 60 to negative 40 dBu. When dealing with amplifiers and powering speakers, we can get all the way up to positive 40 dBu. So the entire measurable range of dBV is negative 60 all the way up to positive 40, with 0 dBV being roughly in the middle. So what are dBV and dBu? They're measurements of electrical signals produced by analog audio equipment, with dBV being the consumer grade measurement and dBu being the professional grade measurement. Next, we'll get into dBFS, also known as dB full scale. This will probably be the most common dB reference you'll see when measuring in digital audio. Unlike its analog counterpart, the dBu, which can span from negative 60 to positive 40, dBFS has a maximum range or a maximum digital limit of 0 dB. Anything over 0 dBFS will distort or clip the audio, and we'll get into clipping in a later lesson. If you're working with a computer, you're working in dBFS. If you're working in analog, you're probably working in dBu. When looking at an analog mixing console, we'll see a lot of VU meters or voltage unit meters, and these are typically calibrated in dBu. When recording with computer software or anything digital like a digital console, we'll be working in dBFS because this is a digital domain and our maximum digital limit is referenced by dBFS. The entire measurable scale for dBFS is negative 100, otherwise indicated by an infinity symbol, all the way up to 0 dBFS. Instead of looking at dBFS like a physical measurement of air pressure or electricity, we can look at it more of the computer's ability to replicate the audio. Important side note, the majority of digital audio workstations will label their dB strictly as dB, even though they are using dBFS. It's important to understand that when you're working in a digital domain or a computer, we're primarily working in dBFS because dBFS is the maximum digital level. I'm not putting the equation up for dBFS just yet because the equation for dBFS utilizes bit depth information, which is going to be a lesson dedicated to itself. So what is dBFS? dBFS is a digital scale which indicates the minimum and maximum level that a computer or a digital console can reproduce, with its lowest measurement being negative 100 or infinity, all the way up to 0 dB. Again, the important thing to understand about the dB is it's a ratio between two powers, whether it's in air pressure, electricity, or in the computer domain. All right, look at that, you made it out alive. We just covered a lot of numbers and math, but it's good for you. If you've made it this far in our lesson series, you know more about audio than most people. The most complicated part of this lesson is over. So with all that heavy lifting that we just did, let's get into some easier things to understand. Now we're going to talk about amplitude. So in our first lesson, when we were talking about frequencies, we discussed how every cycle of a frequency has a positive and a negative amplitude, but we never discussed how we measure that. We actually measure amplitude in the decibel. And to keep it simple, the lower the amplitude, the lower the decibel. The higher the amplitude, the higher the decibel, regardless of the variation of decibel you're using. For example, sitting in a quiet room would measure around 40 dB SPL. If I were to measure myself whispering in my closet, this is me whispering in the closet. So right now we're sitting around 60 dB. As whereas the average rock concert sits around 90 to 120 dB SPL. You can say that the silent room had a lower amplitude than the rock concert, and that the rock concert had a higher amplitude than the quiet room. Another example of a low amplitude sound would be somebody tapping a pen on a table. Another example of a high amplitude sound would be an airplane taking off. A low dB measurement is equal to a low amplitude. A high dB measurement is equal to a high amplitude. A high pressure change will result in a high amplitude, and a low pressure change will result in a low amplitude. Easy enough, right? So what is amplitude? At its base, amplitude is just the measurement of how loud something is. The louder it is, the greater the amplitude. The quieter it is, the less the amplitude. So now that we've covered the dB and amplitude, now let's get into that buzzword, dynamic range. So what is dynamic range? Dynamic range is the relative distance between two measurements in dB, regardless of what variation of the dB you are using. For example, if somebody was talking in a room and it measured around 60 dB SPL, and then we measured a rock concert that was at 120 dB SPL, this would be 60 dB of dynamic range between them. Another example is if the computer's reading on channel 1 is negative 30 dBFS, channel 2 is reading negative 10 dBFS. This would be a difference of 20 dBFS in dynamic range. So imagine this scenario. We're at a studio recording a band on an analog mixing console, and we notice that when the singer is singing a cappella, the VU meter stands around negative 15 dBu. And once the rest of the band starts playing, we watch the VU meter jump all the way up to plus 2 dBu. This would indicate that there's a total of 17 dBu of dynamic range between the quietest part of the song and the loudest part of the song. This is the fundamental principle of dynamic range. So what is dynamic range? Dynamic range is the difference between the quietest sound and the loudest sound. Or, in other terms, dynamic range is the difference in dB between the highest amplitude and the lowest amplitude. The greater the distance between the two measurements, the greater the dynamic range. The smaller the measurement, the smaller the dynamic range. If you found any of this information valuable or you have any more questions, feel free to leave a comment below. If you want to read more on the topic, head over to WavSpot.com. I have all of the illustrations for this lesson there.